Today we're going to be talking about plastics, where they come from, how they're made, and recycling. Plastics, also known as polyolefins, are hydrocarbon chains that we use in our everyday life. Poly means many, ole means that it comes from oil. So that tells you that plastics come from crude oil. How do we get hydrocarbons from crude oil? First, there's an extraction process. Crude oil and natural gas are extracted from the earth, and then they go to a refinement plant where the crude oil and natural gases are broken down into smaller molecules. These molecules include ethane and propane. Then a process called cracking removes hydrogen molecules in order to form a double bond, thus leaving us with ethylene and propylene. Ethylene and propylene are the two main olefins used in the production of plastic. These molecules are considered raw materials or starting materials in the chemical industry. Another raw material that can be used to make plastics is called ethylene glycol. We'll talk more about this molecule near the end of this video. Plastics are just long chains of fairly simple molecules. So we talked about ethylene and propylene. Here we can see that we have an ethylene monomer, which means individual piece. They used to use high pressure and high temperature in order to polymerize or combine these monomers into polymers. But now in the industrial era, we have catalysts, which makes this chemical reaction possible at room temperature. The little n next to the monomer indicates how many of these subunits are in the polymer. So n can be any number. It can be 5, it could be 10, it could be 100 long. But it indicates how many of these little pieces are in the entire chain. A common catalyst used in the plastic industry is the Ziegler-Natta catalyst. I just wanted to introduce you guys to a catalyst that is often used in the plastics industry. There are countless types of plastic, so an identification system had to be made in order for recycling plants to differentiate between what plastic was used to make different materials. This identification system is called the resin identification code. That's the numbers that you see inside these recycled triangles. There are 6 main types of plastics that are most commonly used, and then plastic number 7 is a catch-all for the rest of the plastics or mix of plastics that aren't so commonly used. Plastic 1 is polyethylene terephthalate, or PET, or PETE. Polyethylene terephthalate is the most common plastic that we encounter in our daily life. Some properties of PET is that it's a good moisture and gas barrier, which protects the contents inside from contamination and spoilage. It has high heat resistance, and it's microwave transparent, so the microwave can still heat up the food inside the plastic. This is the structure of the monomer used to make PET. You can see the aromatic ring in the middle, which gives the polymerized plastic a more flexible nature. Some examples of PET products are water bottles and juice jugs, fruit containers, and TV dinner trays. Plastic 2 and 4 are made of the same thing but differentiated by density, so I'm going to go over them together. Plastic number 2 is called high density polyethylene. This type of plastic is far more rigid and has a higher chemical resistance than the other plastics. HDPE is made of ethylene monomers that are polymerized into long chains. As the name suggests, high-density polyethylene has long chains closely packed together with minimal branching. HDPE bottles are often used to store chemical reagents and commercially sold chemicals. Other examples of HDPE are shampoo bottles, milk jugs, truck beds, and the caps of most bottles are made out of HDPE. Plastic number 4 is low-density polyethylene. Some properties of LDPE are its waxy surface, low melting point, and its ability to stretch and flex. It's distinguished between HDPE by the branching of the polyethylene chains, making the chains packing less dense. Because of this branching, LDPE is flexible and can stretch. One of the most common LDPE products we encounter are plastic grocery bags. Bubble wrap is another example of LDPE, garbage bags, as well as Ziploc bags. Plastic 3 is PVC, or polyvinyl chloride. PVC is harder and more rigid than the other plastics. It has the ability to withstand weathering. The plastic is also able to maintain its structure over a long period of time. The structure is a vinyl group, which is the CH2 bonded to the CH, with a chloride attached. We all know about PVC piping, but PVC is also used for synthetic leather, some teething rings, and credit cards are made out of PVC. I also wanted to touch on saran wrap here for a second, because its chemical structure is very similar to PVC, except it has very different properties. This type of plastic is called PVDC, or polyvinylidene chloride, and has 2 chlorides attached to the monomer instead of 1. Plastic number 5 is called polypropylene. Propylene has a high melting point, is generally translucent, and is hard but flexible. We talked about propylene earlier in this video, and the structure of polypropylene is just chains of propylene monomers strung together. Examples of polypropylene are potato chip bags, prescription bottles, but just the orange part is usually made out of polypropylene, and the caps are usually made out of HDPE. Sanitary pads and disposable diapers also use polypropylene in their production. Plastic 6 is polystyrene. Polystyrene can be rigid or foamed. It's hard but brittle and is affected by fats and solvents. This is the structure of polystyrene. The many aromatic rings allow air to fill the gaps of the final product. When polystyrene is foamed, it makes styrofoam. I took a clip from the hydraulic press channel to give you an idea of how much air is actually in this styrofoam.
And here we go. Ah! That's so great. Okay, hey, let's keep it here for a while. I have theory that it has to stay down, let's say 5 minutes, otherwise it just grows back. So we're going to wait like 5 minutes, and it's now 270 bars, so 2.7 kilometers. Okay, I think it's ready, and now moment of the truth, will it grow back? No, it didn't. Yes. Yes, yes. Let's open the chamber. Here is the full size cup. And it's pretty hard. It's not brittle at all. And this doesn't work with all the styrofoam items. If you have larger pieces like these penguins, the size difference ain't so large. And I think you need the thin walls that this has, and then more time.
Finally, we have plastic number 7. Plastic 7 is a catch-all for materials that are made of a mixture of the previously mentioned plastics or anything else that just doesn't categorize as 1 through 6. Plastic 7 also contains some products that are considered green plastics. Polylactic acid is a plastic that falls into this category. It's also called PLA. This is the structure of lactic acid, and it gets polymerized into this chain. You notice that this plastic contains oxygen to carbon bonds instead of having solid carbon to carbon backbone. This allows nature to be able to break apart the plastic a little easier. PLA is considered biodegradable, but it can only be degraded in very specific and controlled composting environments. PLA is currently used as a medium for 3D printing. Polyvinyl alcohol is another plastic that I felt it was important to talk about. This plastic is actually water soluble, which means that it dissolves in water. It's used for things like detergent pods and seed tape. I wanted to introduce you to this plastic because of an article I read in the American Chemical Society's magazine, C&EN. Because the plastic is water soluble, we assume it just goes away once it's dissolved in the water. However, a study showed that wastewater treatment doesn't completely remove it from water before it's released. This allows the plastics to seep into waterways and soils, carrying with it toxins. In the same article, they reference a study showing the presence of microplastics in breast milk, and in trying to find out how these people had microplastics in them, they found no significant links in the products they use or the food they ingested, suggesting that exposure to microplastics is inevitable. Now that we know where plastic comes from, how it's made, and the uses of plastic, let's talk about how much of it is actually recycled. These are rough percentages of how much of each plastic is recycled. The two most commonly recycled plastics are PET and HDPE. Roughly 36% of PET is recycled annually, and HDPE is roughly 30 to 35% recycled. HDPE is the easiest plastic to recycle. Coming in third place is polystyrene. Polystyrene is harder to recycle because the air needs to be removed in order to get down to the core material. The rest of the plastics are rarely recycled because they require different processing. These processes tend to be more costly and very little profit is made from them. This discourages the recycling industry from even doing it. There are two main ways that plastics are recycled. Right now, the most commonly used method is mechanical recycling. Plastic waste is collected and then sorted. The majority of the sorting has to be done by actual humans, which adds more cost to the process. But automated systems are becoming more prevalent. With the advancement of AI, this part of the recycling process may become more streamlined. Plastic needs to be sorted because much of it is dyed. Buyers of recycled plastics prefer a uniform product instead of a bag of a mix of colors. After the plastic has been sorted, it's grounded into flakes. Then these flakes are washed and sanitized, and then ground again. Sometimes these flakes are heated to form small pellets of plastic that will be used to remanufacture new products. The second form of recycling that's being heavily researched in the industry is called pyrolysis. Pyrolysis is the decomposition of plastics using high temperatures and needs to be done in an environment without oxygen. Pyrolysis is a complicated process in an industrial scale and has many requirements that need to be met to end up with a desirable product. This process is used to make biofuels because the end product is usually a liquid made of the same hydrocarbons that are found in crude oil. A while back when I was researching plastics and recycling, I came across an article talking about an insect that's able to eat plastic. That was my inspiration for actually making this video. At the beginning of the video, I mentioned ethylene glycol. If you go to the Wikipedia page, it shows methods of producing this raw material. And if you click on the biological root section, you see a single sentence saying that waxworms have the ability to degrade polyethylene and then excrete ethylene glycol. Waxworms are an invasive species and are extremely dangerous for bee populations because their main source of nutrition is beeswax. There's a debate in the community about how these waxworms are actually breaking down the plastic as well. This article suggests that the worms have enzymes in their saliva that makes it possible to break down the plastic, while another article suggests that it's actually the bacterial strains found in their gut microbiome that are responsible for the degradation. This article claims that two bacteria strains of significance are an Enterobacter species and a Bacillus species. Both of these articles were published within the past 10 years, so the research is fairly new. Another possible future for plastic recycling is fungus. It turns out that there are numerous species of fungi that have the capability of degrading plastic. This article is a review of dozens of published literature laying out which plastics can be degraded by what kinds of fungus. All the articles will have links in the description. Thank you for watching, and I hope you learned something new.